This is an example of a dynamics problem from chapter 4. So go ahead and read the problem. All right, so in this problem, we've got a rescue, and you can see there's a person there attached with a rope to a helicopter, and the helicopter is lifting them up. There's two scenarios. In one case, the helicopter rises with constant velocity, and in part B, it rises with a constant acceleration of 1.5 meters per second squared. How do we solve this problem? Well, with all force-type problems, the key thing you want to do is identify which object you're going to focus on in terms of their motion. Because for that object, you need to identify all the forces that act on them. In this case, we're given the mass of the person, and so we're going to focus on that person right here. Now, unlike the previous problem, we haven't been given which forces act on that person. It's up to us to figure them out. And so there's two broad classes of forces you can consider. The first one is the non-contact forces. And these are forces that are exerted on an object, the person in this case, without directly being in touch with them or contacting them. If you're on the surface of the Earth, you've always got one important one in Physics 2A, which is the gravitational force. So always consider that first, and if there's a gravitational force, we'll deal with that. Afterwards, we need to go ahead and consider all of the other forces which come in the second category called contact forces. And so the contact forces are only forces that come about by direct touch. So they must touch the object that we are analyzing. So let's go ahead and take a quick look here. Here's the person here, and you can see, well, we've got one force. We've got gravity, right? So we're going to go ahead and do gravity first. Gravity is a force that always points down, okay? So I'm going to go ahead and draw this thing. Gravity is acting on that person and pulling them straight down towards the center of the Earth. Force of gravity, as we write it there. Now we're going to look. So we just got the first one done here. We got the non-contact forces. Next, let's go to the contact forces. What else is touching that person? Looks like the only thing touching them there is the rope, right? And maybe the air, but we've been told to ignore air resistance, so we can ignore that. But we do got to consider the rope. And so the rope can produce a force. It's tugging on the person, right? One way to figure out these forces is to go and look at the table of common forces I have here. And so here's gravity, right? We've got a formula for the magnitude of gravity, how strong the pull is, and a direction always towards the center of the Earth. I've already drawn that direction. For the tension force here, there is no formula for tension. However, we do know that it's parallel to the rope and it pulls away from the point of attachment. So let's go back here. So I'm going to go ahead and draw a little picture of the tension here. And here's the person. So that's where the rope is attached there. And then it pulls straight up, parallel to the point of attachment and away from the point of attachment. So there's your tension. Sometimes we write it like this, or you can write it like this as well. It just depends how you want to do it with a little subscript. Force of tension. All right, now that we've got that there, the next step that we always want to do is figure out a free body diagram for the object. All right, so having drawn our picture, drawn our forces, we've only got one contact force. Now we've also done that as well. So we are on to the free body diagram. Free body diagram, basically, you're going to go ahead and draw an XY coordinate system, and you're going to go ahead and plot all the forces that you've identified in your picture. And in this case, we got a relatively simple picture here. All of the forces, in fact, I'm going to draw them from the origin. They are all parallel to the y-axis, which makes it a little bit easy for us when we're going to figure out the components of these two forces. All right, next step, we're going to go ahead and do a chart to track our forces and our acceleration. All right, so let's fill our table in with the x and y components of these vectors. First thing we notice right away is that there's no x components of the forces, so those are both 0. And let's look at part A here first, all right? Part A tells us that it's rising with a constant velocity. Constant velocity, anytime you hear those words, what this means is that the acceleration is 0. Both components are 0, so we can write those in right away. Finally, we need to put in the components for the tension and the gravity in the y direction. Now, whenever you have a vector that's parallel to one of the component axes, in this case, tension, gravity, both parallel to the y-axis, we can take the magnitude, right? How do I write the magnitude? I just take the arrow off. That's how long that vector is, right? Same with this one here. There's the magnitude. When you have a vector parallel to a single axis, all of that magnitude goes into that axis. But you got to decide whether it's in the positive, negative direction, right? So this one is down. And the force of gravity, sorry, got that wrong. That one points up, the tension force. And the gravitational force points down, right? So we've got our magnitudes in there now. Can we come up with a formula to calculate the value for either of those two? Well, going back to our summary of common forces here, we see for gravity, yeah, we can calculate the force of gravity Fg is equal to the mass of the object times the gravitational acceleration constant. So let's calculate that. So in this case, Fg, the force of gravity, the magnitude, it's the mass of the object times g. And in this case, we know what the mass of this object is. It's 70 kilograms. We know what g is always 9.8 meters per second squared. And if we plug that in, we'll get the force of gravity, the magnitude in newtons. And so I get for that 686 newtons. By the way, something that people confuse a lot is sometimes the difference between mass and what we call weight. The mass is just m, how many kilograms, right? This here, the force of gravity, the magnitude of that is what we call the weight. Okay, right? So the weight depends on the acceleration of gravity at the surface of the Earth. If you go to the moon, for example, g is a smaller number and you have a different weight. That's why astronauts are so bouncy on the moon compared to the Earth. All right, so let's go ahead and put our number in here for Fg. So this guy right here, let me erase this. It's going to be a negative 686 newtons. And it looks like we got all our values here except for Ft. This is what we're trying to solve for, right? Let's go ahead and do it. We're going to go ahead and use Newton's second law in the y direction, right? So the second law says the mass multiplied by the acceleration component, this is y direction. Do that a little better here. Is equal to the sum of all the forces along that component direction. In this case, we've only got two forces, right? We've got mass acceleration is equal to Fgy plus Fty. Okay, and we know these numbers, we can plug them in. Acceleration is 0, so that whole side is gone. Fgy, that's this number right here. Plug that in. So we got a minus 686 newtons plus Fty. We don't know what that is, but we know that it's equal to the positive magnitude Ft. And if we solve for Ft with some algebra, we'll come up with an answer. It's equal to 686 newtons. And so in part A, there is our answer. Let's see what this looks like for part B, okay? So I've set this up again for part B, but now we have a different acceleration. It's no longer 0, so we can erase these. And we're actually told, if you read the problem up here, that the acceleration is a constant 1.5 meters per second squares rising, which means upwards, right? How should we modify this picture here? Well, what I do is I always draw the acceleration, but I don't put it on the free body diagram. I put it nearby. So we know the acceleration is up, and there's your acceleration vector. We know the magnitude of that acceleration vector is 1.5 meters per second squared. I don't put that right with the force free body diagram because I don't want to think that the acceleration goes with the forces, right? The forces are separate in Newton's second law, and they're up here. All right, so now I probably also need to modify a little bit the length of my tension force, because we know that the tension, if it's going to go up here, if it's going to cause an acceleration, it's got to be bigger than the downward pull of gravity. It's got to be winning. So it's a longer vector than what the downward pull of gravity is in this case. All right. Again, now we're going to go ahead and do what we've done before. So do we need to modify any of the numbers for gravity or for the tension? Look at the picture. Nope, we don't need to, because mg has not changed, right? This is still, force of gravity is mg, and the mass and the gravitational constant g are the same, so this remains exactly the same. Good. And the force of tension, well, that's a new number. It's bigger. We see the arrow, but we still have all of the magnitude pointed upward in the y direction, so we can leave that there. What about the acceleration? If we look at our acceleration vector, we can see that it's a vector that has no x component, so that's 0. But it does have a y component. It points up, so it's positive, and all of the magnitude of that vector goes in the positive y direction. From here, we're going to go back and feed this data into Newton's second law again. So the mass times acceleration in the y direction is equal to the sum of the forces in the y direction. And again, right, acceleration, I'm going to feed that in there. And the forces, we're going to take these guys here and feed them in there. So the mass, we know what that's equal to, 70 kilograms, multiplied the acceleration, a sub y, there it is, 1.5 meters per second squared, positive. That's equal to the sum of the y components of force, right? And so we have, don't know what Ft is for the Fty, but it's plus Ft, so we can write that down. Plus we've got a negative 686 newtons. And now we need to do a little bit of math here. So let's go ahead and do it. 70 times 1.5 or 1.5, that's going to be equal to 105. And then the kilograms times meters per second squared, that gives us a newton. Over here we're left with the unknown magnitude of the tension force minus 686 newtons. And then we need to just do some algebra here, right? So let's go ahead and add this number to both sides. And when we do this, reversing the direction of the equality, we'll find out that this is equal to 791 newtons. And again, we can kind of see in a sense that in this case, right, the downward magnitude of gravitation, 686 newtons, the upward magnitude of tension force, 791 newtons. That's why it's got a longer arrow, and that's why it's unbalanced and it's producing this acceleration upwards.